In this video, we're going to discuss how to solve simple linear inequalities. We're going to write the solutions both in set notation and interval notation, as well as graph them on the number line. So if you haven't watched the videos pertaining to those topics, you'll want to watch those first. Alright, so when we solve an inequality, it's almost the same as when we solve an equation. There's just one little extra caveat, and some of you probably already remember what that is. But I wanted to examine why that is. Why do we have that extra rule that's different from equations? So with an equation, we know that we can do the same operation to both sides, and the two sides will still be equal. Or in other words, the statement will still be true. So let's kind of examine what happens with an inequality. So say I want to add the same number to both sides. So I'm starting with a true statement here, right? So 2 is less than 6. That's a true statement. What I want to see is if I do the same thing to both sides of the inequality, is it still a true statement or not? Well, it looks like if we add a number to both sides, we still get a true statement. 5 is less than 9. That is a true statement. So adding number to both sides, good to go. If we subtract the same number from both sides, let's see if it's still true. -1 less than 3. That's a true statement. So we can subtract the same number from both sides as well. Alright, if I multiply both sides by 3, I have 6 is less than 18. True statement. And if I divide both sides by 3, I have 2/3 is less than 2. Also a true statement. Now, subtracting is really just adding, but you're adding a negative, right? So we basically looked at adding a positive number and adding a negative number, and both of those resulted in a true statement. We looked at multiplying and dividing by a positive number, but not by a negative number. So let's check that out. So if I multiply both sides by -3, I'm a little short on space here, but I'm multiplying both sides by -3, then I have -6 on the left and -18 on the right. So some of us have been taught in the past, I'm sure, right? When you multiply by a negative, you change the sign. But why is that? Well, if I keep it the same, it's not a true statement, right? Here's 0. -6 is going to be closer to 0 than -18. So, yeah, it's just a false statement the way it's written right now. Right? -6 is actually larger than -18. So that's why we change the sign direction when we multiply by a negative. Now it's a true statement. Same thing if we divide by a negative. So if I divide by a negative, again, I'm starting with a true statement, right? 2 is less than 6. That's always true. But if I divide by a negative and I keep the sign the same way, that's false. Right, here's -2/3. Right there approximately. That's not less than -2. Remember, the smaller number is going to fall farther to the left. So we have to change the direction of the sign because when those negatives are introduced, it changes things as far as which number is larger. Okay, so other than that little extra step, it's going to be just like solving equations. If you have denominators, feel free to multiply both sides by a number to clear them. If you have parentheses, you're going to need to distribute like we have here. And then we'll just keep going as usual. So combine some like terms on the left side. And then add and subtract appropriately to get our x terms on one side and our constant terms on the other side. It doesn't matter which side you put the variable on and which side you put the constant terms on. A lot of people prefer to put the variable on the left, and you'll see why in a minute, but it works this way too. So I wanted to show you this. Okay, so I added x to both sides. I got my x's on the right, so I'm going to subtract 1 to get my constant terms on the left. So I have negative 9 is less than or equal to 3x. Okay, so focus on the term with x. It's a 3x, so to get x by itself, I have to divide by 3, right? So sometimes we get confused when we see negatives in the problem, and do I have to flip the sign? Focus on what operation you're doing. What do I have to do to get x by itself? Well, it's a positive 3, so I'm dividing by positive 3. So the sign stays the same because I divided by a positive number. Now, sometimes this trips people up a little bit with the variable on the right. There's a couple ways you can kind of make sense of that. If you want to rewrite it with the x on the left, then you just have to make sure that, as some of us learned in grade school, the alligator mouth is still open toward the x, right? So that's one way to look at it. Make sure that, you know, the sign is matching up. Otherwise, if you don't feel comfortable doing that, you can kind of, when you go to graph this, you can kind of test some numbers. So, you know, put in a number like 0, right? Is negative 3 less than 0? Yes. But if I put in a number on the other side of negative 3, so here's my number line, right? So 0 is over here. 0 works. That's good. But if I pick a number to the left, like say negative 5, no, that's not true. So that's one way to tell if, you know, you've got this kind of situation where the variable's on the right and you're not sure, okay, am I shading to the left or to the right of negative 3? You can test a number on either side and see which one works. So anyway, basically though, we have this that we're graphing. So in set notation, we would write the set of all x such that x is greater than or equal to negative 3. And in interval notation, we would write this interval. Now, the only other thing that we might run into is sometimes we are, you know, doing the same thing to both sides, working on solving for x, and all the x's disappear. And so if all the x's disappear, then we'll just have a number on each side. So what does that mean? Well, keep in mind what this means here. When there's a variable, the variable can take on different values. If I plug certain values in, I get a true statement. If I plug other values in, I get a false statement. So whether the statement is true or false depends on what value the variable is taking on at that point. If you get rid of the variable, then the statement is either always true or always false. It doesn't matter, you know, what you're planning for the variable to take on if it's disappeared. So, like our statement here, 2 is less than 6. Right? That was always true because there's no variable. So, let's look at this example here. So if we solve this for w, so I'm going to distribute and combine like terms on the left. And then, just like usual, okay, I've got w's on both sides, right? So if I've got the variable on both sides, I want to try and get them all on the same side. So I'm going to subtract 6w from both sides. But what happens is I get 0 from that on the left side and the right side. So the variable is completely gone. So if the variable disappears, all we got to do is decide, okay, is this statement then always true or always false? In this case, it's always true. And when I say always true, always, I mean, you know, it doesn't matter what w is. So for example, if I go back to the beginning and I plug any number in for w, and then I simplify, I'm still going to get a true statement at the end. It might not exactly say -9 is greater than or equal to -9, or it might. Actually, in this case, I think it does. But regardless, I can go back to the beginning, plug any number in for w, and once I simplify, I'm going to get a true statement. So this means all real numbers are solutions. So in interval notation, that's how we write all real numbers. We discussed that in another video. In set notation, set of all x such that x is a real number. Or a third way to write this is this kind of goofy looking capital R denotes the set of real numbers. If you've learned to write that when it's all real numbers, that's fine too for set notation. If we specify interval notation, we're going for the one on the left there. Okay. Now here if we distribute, let's see what happens. Okay, so I've got x's on both sides. I'm going to add 24x to both sides. And again, that completely gets rid of the variable. But now, this is a false statement. Right, 32 is not greater than or equal to 36. So that means if we go back to the beginning, and you can plug any number in for x that you want, and when you simplify, it's going to be a false statement. Doesn't matter what number you choose, you could try all day long. Plug different numbers in for x, and every time you simplify, you're going to get a false statement. So that means there's no solutions. Remember, a solution is a number we could plug in for x that would make the statement true. Well, we can't get this statement to be true no matter what we try. So no solutions. We don't really have a way to write no solutions in interval notation. In set notation, sometimes we use empty braces or the null symbol, which is a circle with a slash through it. So, you know, any of that is fine for denoting no solutions.